The basics for computers as we know them today begin with the telephone industry in the form of fast-switching circuits that, by electromechanical means, selected the line you wanted to contact. Later, circuits were developed with vacuum tubes and then with semiconductors. This paved the way for microminiaturization, in which large quantities of components were integrated in a small space. Creativity helped design some ingenious components that were able to perform amazing operations, such as decision-making and the automation of complicated machines. These components are known as logic circuits. The first ones capable of working in a continuous and reliable way were made of small blocks of plastic material that contain integrated circuits connected to their external terminals by means of thin gold wires. The decision-making is achieved by using a simple language based on binary numbers, which consist only of two digits, 1 and 0. The number 1 represents an action, and the number 0 represents an inaction. It can also be visualized as if the number 1 represents a switch turned on and the number 0 represents a switch turned off. So a decision can be a yes or a no, depending on the response of the circuit to the input signals, which, of course, also are ones and zeros. There are several basic types of logic elements, also called logic gates, which perform various functions. Right now, we will only consider a few logic gates in order to become familiar with this type of circuits. Let's consider the logic gate called AND, meaning together with. In the upper left part of the screen, we have the symbol for this type of gate. It has two terminals on the left side, identified as A and B. These terminals represent the inputs to the circuit. On its right side, the gate has one terminal marked with the letter C, which represents the output of the gate. The table at the upper right is called truth value table, or simply truth table, for that particular logic gate. In columns A and B of the truth table, we have the various conditions present in the gate inputs, and in column C, we can see the response of the gate to the input signals. An AND gate will produce an output of 1 when both inputs are receiving a 1. That is, the output of a 1 requires that the input A and the input B each receive a condition of A1 each. If only one input receives a number 1, the input at C will be 0. The truth table illustrates this behavior. If A and B are zeros, C will be a 0. If A is equal to 0 and B is equal to 1, C will be a 0. If A is equal to 1 and B is equal to 0, C will be a 0. Finally, when A receives a 1 and B also receives a 1, C will be a 1. We see then that in order to get an output of 1 in an AND gate, both the A input and the B input must get a 1 each. Another type of basic logic circuit is the OR gate, meaning one or the other. We can see the symbol for this type of gate. In an OR gate, an output of a 1 results if one of its inputs or both is a 1. The corresponding truth table appears to the right of the OR gate symbol. The truth table illustrates this behavior. If A and B are zeros, C will be a 0. If A is equal to 0 and B is equal to 1, C will be a 1. If A is equal to 1 and B is equal to 0, C will be a 1. By the same logic, when A gets 1 and B also gets a 1, C will be a 1. There is a variant to the OR gate, which produces an output of 1 when only one of its inputs gets a 0, but when the two inputs get a 1, it produces a 0. The symbol for this gate is similar to that of the OR gate, except that an additional curved line across its inputs indicates this condition of exclusive. An additional component in the arsenal of logic gates is the circuit named NOT. This circuit has only one input and produces an output of 1 when it gets a 0 in its input. However, it produces a 0 when it gets a 1 in its input. This component can be inserted at the output of an AND gate to form a gate called NAND, not AND. By the same token, it can be inserted at the output of an OR gate to form a gate called NOR, not OR. The gates thus formed behave normally, except that the additional NOT component reverses the output from that expected from the normal gate. As an example, let's take a look at a NAND gate, AND combined with NOT. On the upper left side of the figure, we see the case when one input is a 1 and the other is a 0. The AND circuit of the gate will deliver a 0, but then the NOT component will change that 0 into a 1. These differences will be reflected in the truth table for this gate. The same thing happens if we add a NOT component to the OR gate. In the case of an OR gate in which one input is a 1 and the other is a 0, the OR circuit of the gate will deliver a 1, but then the NOT component will change that 1 to a 0. A remark about the symbols is that it is not necessary to draw both elements of the NAND gate, and it is enough to draw a small circle and replace the word AND by NAND, which indicates the presence of the NOT component. In the case of the NOR gate, proceed in the same manner, drawing a small circle and replacing the word OR by NOR. To conclude this brief explanation, it is a good idea to provide an example. Suppose we have a dog named Maxie, and he is usually in the yard of our house. Maxie is in the yard waiting for the door to open. During daytime, a sensor on the top of the wall produces a 1 when the sun is shining. Otherwise, the output of this sensor will be a 0. Just below, we have a sensor which checks the temperature outside. When the temperature is nice, the sensor produces a 1. Otherwise, the output of this sensor will be a 0. Farther below, we have the door opening mechanism for allowing Maxie to enter the house. The door opens when the mechanism gets a 1. Let's assume the door closes automatically several minutes later, just for simplicity. What kind of logic circuit can perform this task? The simplest way to achieve this is with an NOR gate. Let's follow the sequence. During daytime, the upper sensor produces a 1, indicating the sun is up. This causes the OR gate to produce a 1, which is inverted by the NOT component. Therefore, the door opening mechanism will not operate. After nightfall, the sunlight sensor delivers a 0, And if the weather is warm, the temperature sensor will continue to produce a 1. Thus the OR gate will continue to deliver a 1, which the NOT component will convert into a 0. The door will still be shut. When the temperature drops to an uncomfortable level for Maxi, the temperature sensor will produce a 0, which the NOT component will convert to a 1. The door will now open. We will have a small robot that will not let Maxi into the house during the day and automatically let him in when the cold weather endangers his health. I hope this video has been useful to you. Thanks for watching and please subscribe to my channel.